I'm Keith Cambron. I'm a retired communications engineer and amateur radio operator. This presentation, I'll describe signal-to-noise ratio, how we measure it, and how it affects digital modes as well as CW and phone. My reason for preparing this presentation is I've seen a lot of information on EHAM and other blogs about how signal-noise ratio is measured, and in particular, how it's reported by some of our software like WSJT-X. This is the rig I have. It's an ICOM 7600, and I'm going to explain very simply at a high level how the signal-noise ratio affects decoding, and then I'll get into much more detail later on. The ICOM 7600 receives the signal off an antenna. All the digital modes, as far as I know, are always modulated in upper sideband. The ICOM 7600 has a particular upper sideband setting called D1 through D3, which allows you to customize how you're going to actually receive that digital signal. After the digital signal has been demodulated, it'll appear as an audio signal on the USB connection to a computer. That computer will be running a application program such as WSJT-X or a PSK31 program, and it'll take that audio signal and it'll filter it and decode it. So this is what's happening. We get the RF signal, the ICOM 7600 or your rig will filter and do the demodulation, and that'll produce an audio stream. That audio stream is sent to the computer where it's further filtered by the decoding program such as WSJT-X, and then it's decoded and you'll see text appear on the screen. So let's step back and define what signal-to-noise ratio is and how it's measured. This is a very simple diagram. We have a communications channel. There's a very specific definition for a communication channel. In the case of the primary mode I'm going to be talking about today, which is WSPR, Weak Signal Propagation Report, we're going to find this channel is only 6 hertz wide. So that channel is bounded on either side. In the case I've shown what are called brick wall filters, but of course we can't implement them from a practical viewpoint. We'd see more of a bell-shaped curve here. But theoretically, we have a communications channel. A signal is in that channel, and it rides on top of noise. Now, the noise we'll be talking about in this presentation is Gaussian noise, or you may know it as thermal noise. It's a noise that's present in the environment, and it's also present in your radio. But the discussion of thermal noise and its Gaussian attributes are beyond the scope of this presentation. We'll just assume that that's what we're talking about. You'll hear it as a constant hiss in a radio. So the measurement for signal-noise ratio is the power of the signal in watts divided by the power of the noise, again in watts. As an example, if the signal power were equal to the noise power, we'd have an SNR of 1. But signal-noise ratio is usually quoted in decibels, where the signal-noise ratio in decibels is equal to 10 times the log to the base 10 of SNR. So in our example, where the signal power and the noise power are identical, we'd have an SNR dB of 0 dB, because the log to the base 10 of 1 is 0, 0 times 10 is still 0. Whisper modulation is used in this presentation and all my measurements, and the reason I chose that is because it's a beacon service. I can measure from time to time. I can take successive measurements on a transmission, and the transmitter will just keep transmitting. So I can do a comparison across time of various filters I'm going to use on the 7600 and take a look at how signal-noise ratio changes. This is a very robust form of modulation. It has a standard message. The operator does not populate the message. It's always the same. It's got a call sign, 15 bits for a locator grid, 5 bits for the power level, and 2 bits for message type. So the information bits are 50. And we're going to talk about information bits at some length today, and that's really the measure that we're going to focus on, how much information is transmitted in any one particular mode. But because this is a weak signal modulation scheme, it has forward error correction, so it ends up with a total of 162 bits. That is, for every information bit, there are 2 more forward error correction bits. That allows the receiving side to decode this in the face of impairments. That is, if some of the bits in this 162-bit message get flipped from zeros to 1 or vice versa, we can still decode it using forward error correction. The transmission whisper is upper sideband, and in the baseband, that is the audio band, it's centered on 1500 hertz. It uses 4 frequency shift keying channels, that is 4 separate tones are used. 1 tone is transmitted at a time. The total channel bandwidth is 6 hertz, which means that each tone is about 1 1/4 hertz spacing. And of course, this is only possible because we use digital signal processing to filter and decode this, something that couldn't have been done 30 years ago. The band where all whisper transmissions are expected is 200 hertz wide. So 6 hertz channels and 200 hertz wide band yields 33 channels within the band. Because this is such a robust transmission mode, we can use very low power, 5 watts or less. And as I said before, the power level that's transmitted is actually encoded in the standard message. And we'll find that 5 watts is equal to 37 dBm. It takes 110 seconds to send those 50 information bits. So it's almost 2 minutes to send 50 bits of information. That yields an information bit rate of less than half a bit per second. So it's a very slow form of transmission. And we're going to see why that's important when it comes to weak signal propagation in a later slide. How would we measure whisper's signal-to-noise ratio in an ideal situation? Well, we have these channels, and there are 33 of them in our 200 hertz band, and ideally, we would measure the power of the signal and divide that by the power of the noise. So here I've shown this as the power of the signal in green and the noise power in red. We would do that for every channel within the band. We would expect to get very different answers from each of the channels depending on the location of the operator and atmospheric conditions between the transmit and receive stations. But this is ideally what we would expect to happen. So here's what WSJT-X whisper capture looks like on my computer using the 7600 as the transceiver. This is the waterfall display, and here we see at 1500 hertz, and this is an audio signal that's being received, filtered, and decoded by WSJT-X. We see the waterfall in the various channels that are operating within that. So these streaks that we see coming down here represent the 6 hertz particular channels that are transmitting. In the scrollable decode display, we have the time that the signal is received. We have the decibels. People call the signal noise ratio, and we're going to find out that while we can use that as a measure of merit, it's really not the signal noise ratio of the signal. The delay time, these transmissions are done at fixed interval, and they're based upon universal time clocks. So this is how much the transmit and receive differ from that standard. This is the frequency of the transmitted signal, received signal, and we see that they're only different by a few hertz. And that's what we expect, since these communication channels are only 6 hertz wide. The drift is how much frequency drift. We can't afford very much frequency drift because this channel is only 6 hertz wide. So that's a measure of the drift between the transmit and the receive transceivers. These are the call signs, which you recall is embedded in the 50 information bits. The grid, which is also embedded, and these are 4-digit grids. They don't transmit 6 or 8-digit grids. And this is the transmit level as encoded at the transmitter, not measured at the receiver. So the transmitter for this particular transmission right here is saying they're transmitting at 30 dBm, which is slightly below the 5-watt maximum that's recommended. This is the distance between the transmitter and the receiver. This is computed by WSJT-X and is not part of the message that is in the Whisper standard message. This is an important slide because it's critical that we understand how the filtering is done. If we think at a high level, think about the end process that's going to have to be done. The WSJT-X running on our computer is going to have to take the information from the sound card, which is audio. It's going to have to perform an A to D conversion, run it through DSP, digital signal processing filters, and then demodulate it. So our goal in the 7600 is to deliver to the computer in WSJT-X the best audio that is most suitable for this process. So let me back up to where the signals received. We're going to go through a bandpass filter and an amplifier, and then a first mixing stage to get us to the intermediate frequency, the IF level. There we're going to use something called a roofing filter. Now, I know most of you are familiar with that, but I'm going to go through it for the operators that may be new to this. And then we're going to go through a second mixer that will take us down to baseband. In this presentation, I've designed 2 filters that will be used to filter the baseband audio, F1 and F3, and I'll describe those shortly. But our goal, again, is to deliver to the sound card the best possible audio to make this efficient and as error-free as we can make it. The ICOM 7600 is a capable receiver, and it allows me to build specific audio filters for the baseband audio signal that we're going to pass to the computer. So here I've designed 2 filters, filter F1 and filter F3. So filter F1 is what you might typically use for upper sideband. It's kind of a default in many radios to be 2.6 kilohertz, sometimes 3 kilohertz wide for upper sideband audio. So I've used a 3.6 kilohertz filter, but the DSP software in the 7600s lets me modify that. So I've overlaid two 3.6 kilohertz filters so that they intersect and they provide the resulting 2.6 kilohertz filter. So that's the bandwidth that the signal will see. I'm using a roofing filter of 3 kilohertz. Now, let me explain what a roofing filter does. A roofing filter is before the second mixer, and it's meant to filter out as much extraneous signal strength as possible. There are 3 roofing filters in the 7600 that you can select. These are mechanical filters that are before that second mixer stage. In the 7600, you can choose a 3 kilohertz, a 6 kilohertz, or a 15 kilohertz roofing filter. Many of the older radios, the only roofing filter that was available was a 15 kilohertz roofing filter. And that's because they didn't want to filter out wideband FM. But in more modern radios, you have a choice. And because they're mechanical, you cannot modify these. You simply have to pick one. So since we're working with a audio signal, we're going to use the 3 kilohertz filter. So 3 kilohertz is the roofing filter before the mixer. And then after the mixer, we're going to use digital signal processing filters. And we're able to build a 2.6 kilohertz filter for our F1 filter. The second filter is filter 3. We're going to define a very narrow filter. So again, we're going to use a roofing filter of 3 kilohertz, but we're going to select a 50 hertz wide filter. And we're going to center it on 1500 hertz. Both of these are centered on 1500 hertz because that's where the WSPR band is centered. So keep these two filters in mind, and we're going to receive whisper transmissions using the two different filters and see how WSJT-X reports those transmissions. Now, I chose this slide here because I wanted you to hear the difference that the computer hears. This is on the audio stream that's leaving the 7600 and is sent to the computer and to WSJT-X for demodulation. The first signal is the F1 filter, which is a 2.6 kilohertz wide. So we're going to hear all the WSPR, the whisper transmissions, in that band for this particular measurement. Listen to this. Bit noisy. So those are a lot of different channels, 33 channels potentially in that transmission time. That's the 2 minutes that WSPR is transmitting. Using our F3 filter, we're going to be 50 hertz wide. Now that's still pretty wide for whisper because we know that the communication channels are only 6 hertz wide. So we could potentially have 8 channels in this 50 hertz filter, but the ICOM 7600 would not let me build a filter that was narrower than 50 hertz. But listen to the difference with our F3 filter, which is only 50 hertz wide. Now, intuitively, you can pick out which one you think would be easier for the computer in WSJT-X to filter and demodulate. It would be the F3 filter. This is a bit of a detailed slide, but there's a lot of good information. So I captured runs from WSJT-X on using filter 1 and filter 3, and I did it over about a 6-minute period. Now remember, I chose whisper because it's a beacon transmission, which means it's going to be receiving these channels in a serial fashion, but the transmitter is not going to change frequency and it's not going to change the power level. So let's look first at what I captured using F1. That's our 2.6 kilohertz filter. So here are the stations that I was able to receive. I picked these out of a whole list to make it easy to understand in this table. And you can see they were transmitting anywhere from 23 to 30 dBm. So they're running about 3.5 to 4.5 watts. The time stamps are here. So these were collected after actually I did the earlier F3 filter. Now let's look at the decibel, which is described by operators as the signal-to-noise ratio that WSJT-X is reporting. And we see here one signal is down minus 26 dB. Now when I was getting the motivation for this on eHAM, I was listening to two operators that were having an exchange, and one of them said, I got a signal at minus 28 dBm, and the other one was saying, you know, when the computers get fast enough and powerful enough, and we get really good digital modes, we'll be able to detect signals at minus 36 or minus 40 dBm. We'll be able to detect those and decode those. And that really gave me a motivation to do this presentation, because that is not what is happening here, and I can demonstrate it. When I turn around and use the F3 filter, now it's very narrow, I get very different readings in the signal-noise ratio as reported by WSJT-X. So these are the same stations. The readings are only taken a few minutes apart, but the readings are very different for the same stations. The delta for WW0, WWV is a 22 dB difference. That is, with a 50 hertz filter, I'm reporting 12 dB positive, and at the 2.6 kilohertz filter, I was reporting minus 10. So that's a swing of 22 dB. Now, did the operator increase their power by 22 dB? No, they did not. It's the same power. It's 30 dBm. And so did the noise level drop by 22 dB? No, the ambient noise certainly did not drop by that amount. The same is true of the other stations I recorded. On this one, we have a 32 dB difference. At the 50 hertz filter, I measured 11 dB, and with the 2.6 kilohertz filter, I measured minus 21. So there's a 30 dB difference. On this one, K0CFW, I only get a 12 dB difference. Now my ICOM 7600 wouldn't let me build a 6 hertz filter, but we can do a computation to extrapolate what a 6 hertz filter would have measured had it been used in this experiment. And this is the equation that's used to take the results from the 50 hertz F3 filter and translate them into 6 hertz. And what we find is there's an almost 40 dB difference, anywhere between 20 and 40 dB difference between the signal-noise ratio that would be measured with a 6 hertz filter as opposed to a 2.6 kilohertz filter. So what is WSJT-X measuring, and why is it so different than the theoretical chart I showed you at the beginning, where we measured the signal within the channel and the noise within the channel? Well, here's what's going on with WSJT-X. Ideally, if we were measuring the signal-noise ratio of channel 3, we would measure the signal power and we would measure the noise power within that channel. And we would divide signal power by the noise power to get the signal-noise ratio. But that's not what WSJT-X is doing. What it's actually doing is measuring the power in that 6 hertz channel and dividing it by the power across the entire 2.6 kilohertz audio channel. So it's measuring all the power that comes over the audio channel and dividing that by the power in that band. So it's a figure of merit. It tells us something about the signal, but it in no way is the actual signal-noise ratio of that channel. It misrepresents it by anywhere from 20 to 40 dB. So let's talk in a general sense about various modes and what signal-noise ratio each of them require. And this is information that was taken from a website by PA3FWM.NL. And it's a really nice paper on signal-to-noise ratio and the minimum SNR used by various modes. So on the left-hand side, I've listed a variety of modes: voice, CW, RTTY, and so forth. Now, the non-digital modes, which are the first two, PA3FWM estimates, and it's his estimate, and he goes through an explanation of how he got there, that you need these minimum signal-to-noise ratios in a 25 hertz band. And this is certainly subject to discussion, because CW, for example, if you're transmitting at 5 words per minute, you're going to require a much lower signal-noise ratio than if you're transmitting at 30 or 40 words per minute. You would need a much higher minimum signal-noise ratio. Here we just list the bandwidth, and this is the minimum signal-noise ratio as computed by the Shannon-Hartley limit. Now, Claude Shannon and Bob Hartley were two engineers at AT&T Labs back in the 40s, and they were there along with Nyquist, and there was a lot of work done on digital signal processing. The Shannon-Hartley limit is one of the most famous equations that came out of that period, and it sets the maximum information that you can get for a particular mode of transmission. So I is the information in bits per second. W is the bandwidth of the channel in hertz times log to the base 2 of the signal-noise ratio. That's the power ratio, not decibels, but the straight power ratio, watts over watts, plus 1. So here's the minimum signal-noise ratio that is derived using Shannon-Hartley limit. And we see that it's always going to be less than what PA3FWM has given us for the various modes. And again, in voice, you got to translate and make some sort of estimate for how much information in bits per second comes out of a voice transmission. So, this is all a bit conjecture for these two, but it's interesting to talk about. Now we can turn this around and ask ourselves to communicate the equivalent, we can ask ourselves, what would be the power to give an equivalent QSO given these various modes? And that takes into account the signal-to-noise ratio. So if we wanted to compare a 100-watt single sideband voice transmission with CW, we'd find that to get an equivalent reach, we would only need 5 watts. So 5 watts should reach as far as 100 watts would be with phone single sideband. RTTY and PSK 31 both need about 40 watts to be equivalent to a 5-watt CW or a 100-watt phone. Whisper only needs 5 watts, and it has the same reach and intelligibility as a 100-watt phone. Whisper 15 is more robust than Whisper even, and you only need 700 milliwatts. JT-65 is even more robust, and you only need half a watt to be the equivalent of 100 watts on phone. So here I compute the minimum signal-noise ratio for these modes, and I threw in the voice and the CW. And I took the Shannon-Hartley limit theorem, which tells you that the maximum information that you're ever going to be able to get from a signal with a bandwidth of W and an SNR. And I turned that equation around and I said, okay, what is the signal-noise ratio in decibels you need for each of those modes? Now, when you do the algebra, you end up with this equation, and I've highlighted that the key to the computing the signal-noise ratio minimum is 2 to the I over W. What does that mean? That means we can lower the required signal-noise ratio. That is, we can make our transmission more robust by lowering the SNR that's required, by lowering the amount of information we send, or by increasing the channel bandwidth. And that makes intuitive sense. The wider the bandwidth and the lower the information rate, the more robust we can make the mode. So here again, I've listed the Shannon-Hartley limits to these various modes. I've listed the data rates and the bandwidth. And what we see with our most robust mode, JT-65, it only has a data rate of 1.54 bits per second, and that's spread over 200 hertz. So Whisper has 1/3 as many bits, but it's sending those bits over a channel that's only 6 hertz wide. So this channel for JT-65 is about 30 times wider, and it only increases the amount of information by a factor of 3. That's why it has such a low Shannon-Hartley limit of 23 dB. Now I took the minimum SNR dBs that was from the previous chart, and these are supposed to be practical empirical measures of what the minimum SNR is for each of these modes. And I took the difference between those and the Shannon-Hartley limits. And what we find is these numbers. So what this says is single sideband voice is a long way, the minimum SNR is a long way from the Shannon-Hartley limit, which means it's a very inefficient, or it is not a robust form of transmission. CW is 23 dB from the theoretical limit, and RTTY is 16 dB. The rest of these modes are all within about 10 dB of the limit. And it's unlikely that we're ever going to get a lot closer. We might shave 3 dB off of this in time to get to the theoretical limit. But what this dispels is the conversation I saw in EHAM that says if we get faster computers and better modulation schemes, we're going to be able to dramatically improve our ability to transmit and receive signals. That's not going to happen. These modes are highly efficient and they're quite robust. So they're within 10 dB of the theoretical limit. So we should not expect to see a lot of progress with faster computers and new transmission modes. So what are the takeaways from all this? Well, you've learned a bit about theory, you've learned about the Shannon-Hartley theorem and how to compute that. But let's talk about some things you can do in your own operations that aren't based upon doing a lot of computations. Think about the modes that you use, and in particular, the roofing filters that you use. Now, I've just given examples here from the ICOM 7600. Your transceiver may or may not have 3 roofing filters, or it might even have more. So select the roofing filter that will discard anything outside the band of interest before you get to that second mixer stage. Any spurious signals that are outside the band that you're interested in, when they hit that second mixer stage, they're going to create intermodulation products. So you're going to get intermodulation products which are going to generate signals where you don't want them. And that's true because no amplifier is perfectly linear. So one thing you can do with the correct roofing filter is eliminate unwanted intermod signals, impairments. The other thing you do when you use the correct roofing filter is you're going to reduce the dynamic range of the signal. So if you think in the time domain, if you have spurious signals that you're sending to the mixer and onto the audio, then you're going to have a lot of noise, and that's going to increase the peak-to-peak measurement of that audio. That has to be converted in the A to D converter. So spurious energy that goes to the computer is going to result in quantizing distortion. So pick a good roofing filter that fits the mode you're using. If you have a transceiver that allows you to build filters for specific modes, then certainly select the right baseband filter. In the case of digital mode, it's going to be in the audio band for that mode. In particular, if you're a whisper enthusiast, build a 300 hertz filter that's centered at 1500 hertz, and that will eliminate all the other noise around that whisper band.